Okay. I think that fits into a category of another one of these categories of things people know but haven't necessarily thought about in great depth. And so I went back out to the kitchen again, and I've got all sorts of stuff going on. Well, I got a few things going on here. For starters, you can see that I've had this pot of water that I just started heating up.
Mm-hmm.
And there are a couple of things that you know about this. One is, can you see the steam coming off of it yet?
Yes.
Yeah, because it was boiling a few seconds ago, and I imagine it will again here when I start it up. And so here's one of the things that I think all of us know, but don't necessarily think about. For instance, this water is really pretty hot, and I bet that if I were to take my hand and move it in towards here and put it in the water, you would probably start to wince before I even got it in there, right? You can start to see the bubbles coming, right? Oof. So you know that water is hot, right?
Yeah.
Right. I mean, it's 100 degrees Celsius, 212 degrees Fahrenheit, and so I'm not going to put my hand in the water. I'm also not going to grab the metal around the outside here. But down at this end is a handle that's been attached to that pot, that's been touching that water. And for some reason, you're going to have no qualms about me picking it up and just walking around like this, right?
Mm-hmm.
So that tells us one thing. It says that, hey, that water is hot. We know that it's transferring energy to the metal of the pot, and the pot is going to be really hot. And if I grab a hold of it, my hand is going to get really hot really quickly. But down here at the plastic or the rubber end, it's no problem picking it up. And so that tells us that although all of this is really warm, the water is really warm and is transferring energy to the metal. The metal changes temperature and gets really warm very quickly. The handle, this plastic piece down the end, is just not taking up the energy as fast, and it doesn't transfer it to my hand as fast. So the nature of the substance, whether it's water, metal, or plastic, or frankly, hand, and its ability to absorb energy is the nature of the substance actually matters.
Yeah.
Okay. Which, hold on now, 1 second. I wrote myself a note. And so my note says, when we worry about things like thermochemistry and heat transfer and that sort of thing, that the amount of heat is proportional to the amount of it that we have, the mass. This is a specific heat that's designated for a particular substance, and the change in temperature, right? So this substance makes a big difference in terms of how much energy gets transferred and how fast it gets transferred. So in this equation, this constant is designated for any particular individual substance, because each individual substance transfers heat differently. How am I doing?
That makes sense. Yeah. So you're saying that the rubber doesn't really absorb that much heat, which is why you're okay grabbing the pot.
Yes. Yeah, exactly. And well, it absorbs it a lot more slowly from the pot, and it transfers it much more slowly to my hand, right? It just isn't very good at absorbing heat or transferring heat. I mean, it's an insulator, right?
Yeah.
Okay, so same idea. I'm now going to take my pot off the stove, and I'm going to come and put it here on the counter. Actually, I'm not going to put it on the counter, because I know if I put it on the counter, there's a chance I'm going to get in trouble later on when Rebecca comes home. So I'm okay with putting it on this mat. This mat is made out of rubber, and I know that it's not going to transfer the heat from the pot to the counter very quickly.
Correct.
Likewise, I've got this one over here. It's made out of, I think, cork. It's wood or cork or something like that, right? And it doesn't transfer it very quickly. In fact, so all of these substances, like I've got a whole slew of them here. I've got a plastic cutting board. I could put it on that. I've got something made out of wood. I've got a fabric hot plate that's probably made out of wool or cotton or something like that, probably mostly cellulose or something like that. I've got a rubber one. I've got these little grippy ones that I think you're allowed to grab a pot with if you want. And then I got this one that comes along, and I put my hand right up inside it as I need to grab something. But they all have different specific heats. They all have a different ability. They all have a different ability to transfer energy. Okay, I got another one for you. All right, same equation, same problem. So flip it around. All right. So here is this same pot of water. It's been boiling, right? And if I were to dunk my hand in there, you'd wince, right? You'd probably say, no, Will, don't do that. It's a bad idea. And you're right, it would be a bad idea. However, oh, look at this. I've got a metal spoon, and I'm just going to take out of that pot just a little bit of water. Okay? And I'm going to sit down here, and I'm going to put my finger in it. Look at that. Now, was that a crazy thing to do?
Not as crazy as a whole pot of water.
Exactly. Not as crazy as a whole pot of water. Why is that? Because sure, we're talking about water, which has a big heat capacity, but we changed the mass significantly, right? And so the amount of substance, right? Me putting my hand in a whole pot of water has a huge amount of mass. I don't know, there's probably half a liter, right? 500 grams of water or something like that. In my spoon, I had maybe 5 milliliters, 5 grams or 4 grams, maybe even 3, tiny, a much smaller amount. That's why when you're cooking on the stove, oh, I got another pot going here now because apparently I got pots today. If a little bit spits out, oh, I can even put my hand in the steam for a second, right? Not too bad, right?
Right.
Because the actual amount of water that's interacting with my hand is pretty slim, pretty small. So back over here again. So the amount of substance matters, the nature, the type of substance matters, and and this is the amount of the temperature change, right? And that'll tell us how much heat gets moved. Okay, do you want to ask a question or keep on going?
I think I understand the mass and the heat capacity. Is the change in temperature just when you heat something up, or could you explain that a little bit more then?
Maybe. So if I want to change the temperature of water from what I got it out of the tap, so it comes out of the tap maybe at 10 degrees, 15 degrees, something like that, and I want to get it to boiling, I might have a change in temperature that could be 60 or 70 or 80 degrees. In order to get an 80-degree temperature change, I'm going to have to put in a lot more energy. I'm going to have to heat it up for a longer time. If I only want to warm it up a little bit, let's say I want to change its temperature by 50 degrees, then the amount of energy that I have to put into it is going to be different. It's going to be smaller. So the amount of temperature change, the overall change, is proportional to the amount of energy is proportional to the amount of temperature change that I'm going for.
Okay, that makes sense then.
Is that better?
Yep.
Okay. And in an equation like this, it's a nice simple one. So what's present in the equation? If you or I, all of our students, can learn to read an equation for what's present, it's also a little bit interesting to think about what's not present, right? What's absent from the equation. There's nothing in here that talks about pressure, or there's nothing here that talks about volume. There's nothing in here that talks about the day of the week, right? Or the month of the year. This equation is actually very simple. It's only got 4 things in it, and it doesn't have a lot of doesn't say anything about how long the variable is, or so how long the substance is, right? Or what shape the substance is, right? All of those things aren't in the equation. So if you and I and our students can get in the habit of being able to read an equation for what's in it and what's not in it, then that's a pretty useful thing. So yesterday, or a couple of days ago, I can't remember when it was now, Yeah, so yesterday we talked a little bit about the difference between the refrigerator and the stove, right? The stove
Yes.
is a device that provides energy, right? So we know that when I want to heat something up, I put it on my stove, I turn it on one way or another, and it provides energy. In this case, it was providing it to water, and so the water was going from being a liquid. Can you still see the steam rising off of it?
Yes, I can.
Yeah, so we know that going from a liquid to a gas is a process that requires energy, because I'm doing it on my energy providing device on my stove. Okay,
Okay.
so far so good. Now, opposite in my freezer, in my fridge, right? My fridge takes liquid water. Well, here are the ice cubes left over, right? Apparently we used 2 of them last time. So it takes liquid water and turns it into solid water. So that's going in the opposite direction. So liquid to solid is a process that energy has to be removed, because my refrigerator, my fridge, is an energy removing device. Okay?
Yeah.
All right, so now here's where it sometimes gets another place that sometimes gets tricky for students, because in one of those cases we are making bonds, and in one of those cases we are breaking bonds. Okay, so for instance, when I am breaking bonds, I'm doing that with which device?
The stove.
The stove. Right? The stove breaks the liquid water molecule bonds, intermolecular bonds, and drives them in, it drives them into the air as a gas. The bond forming device is the fridge. Right?
Mm-hmm.
Okay, now I want you to think for a second. I don't know who's home at your house, but you could probably do this for yourself. I'd like if you took your right hand and you put it on your left wrist. Okay, now I want you to yank hard enough to pull your arm out of its socket. Right, just rip your arm off right now. Okay, maybe that's not such a good idea, but okay, it's not a good idea, but it tells you something, because your arm is bonded to your shoulder, right, to your body. And
Yes.
in order to break that bond, what do you have to do?
You need to put energy into it.
You're gonna work hard, right? You're gonna have to do some work to rip your own arm off, right? So breaking the bond requires energy, right?
Mm-hmm.
So breaking bonds, stove, requires energy. Okay?
Yep.
So now, by extension, bond forming, like the fridge, is the opposite of that, right? And so it releases energy. Okay?
Okay.
Go ahead and ask a question, because we're about to get into the part that I think is really a challenge for students at times.
So we're talking about phase changes, and so if I got this right, when you're going from a liquid to a gas, or you're heating something up, it requires energy. But
Correct.
if you're cooling something down from a liquid to a solid, the liquid releases energy.
Right. Right. That energy has to go somewhere.
Okay. Okay. So far, we're good. So far, we're
Okay.
good.
All right. So then here's where I think students have a hard time. People have a hard time. And it's with the notion of exothermic and endothermic.
Yep.
Okay, so it's very clear to me. It's very clear to me that over here at my stove, we saw the liquid going to a gas and the steam rising away, right?
Yep.
The problem is, why does it feel so warm over here? Because normally we would think, hey, if it feels warm over here, is this an endothermic or an exothermic process?
You would think it's exothermic because
Right.
it feels like it's giving off heat.
Right. Right. Because I'm over here and it feels like it's giving off heat. But it's not actually the heat of the water molecules going from liquid to gas that I'm feeling. I'm feeling some other heat by the inefficiency of my stove heating up the surroundings and heating me up, right? I'm not part of the steam making process right now. I'm feeling other heat from around the outside. And when I put my hand in the water or in the steam condenses down to a liquid. So it goes from being a gas to a liquid. Hold it. It goes from being a gas to a liquid. That's forming bonds. That releases energy. That's why it feels warm to me. So I'm feeling warm because the steam is becoming a liquid and releasing the energy to me. So it feels to me like it's getting warm, even though I'm looking at a process that my eyes tell me is a process that requires energy. And so our personal experience of observing bond breaking sometimes involves us getting warm. And so we get confused that bond breaking is actually requiring energy. And so that's a place where I find students get confused because they interpret their own experience, ironically, for the experience that the molecules are experiencing at that moment in time.
Yeah, that is really confusing.
Yeah, it's really confusing, right? And so you got to work really hard at it. So that's why I waggle my finger at you, but I got three fingers waggling back at me. That's why it's helpful for me to think about my stove is an energy producing device. That's not confusing, I don't think. My refrigerator is an energy withdrawing device. That's not confusing to me. It's only confusing when I get confused in thinking about how come I feel this weird way, warm, even though I'm pretty sure that my water, going from water from being a liquid to water being a gas, is supposed to be absorbing energy. Shouldn't I feel colder?
That kind of clarifies it a bit more, the way you think about it. That works.
Yeah. Yeah, it's not trivial. Generations of students have struggled with that one. And I have to say, I've taught this concept for many years, maybe for 15 or 20 or maybe even 25 years. And I still have to stop, go slowly, and think it through every time, because my personal sensory experiences tell me the opposite of what actually is going on. And so I have to slow down and try to figure it out.
Yeah, I was a little worried too. I saw the words endo and exo, and I wasn't sure which one was which for a second.
Yeah. I mean, it's pretty easy for most people to get to. Hold on. It's pretty easy for most people to get to exothermic, meaning energy leaving, and then by extension saying that endothermic must be energy going in. But It's hard to wrap that intellectual concept to wrap your head around that intellectual concept when the very fiber of your being is telling you the opposite over by the stove.
Mm-hmm.
Yeah, so that's really that's a bit of a challenge.